This video is actually a remake of one of my old videos. It was one of my most popular videos, and it also caused a lot of confusion. It's on a popular subject, but the way I presented the information was confusing to a lot of people, and a lot of the code I used was not written in the video, which is confusing for people when they're new. I've received a lot of complaints about it, so I decided to redo the video. Also, I'd like to mention that in this video I will be covering the physics of tile collisions, and I'm not going to go really in depth in this video. I knew there was a problem a while back, and I made a video to go in depth on that subject, so I've linked in the description the video that goes in depth on the tile-based collisions. I'll briefly cover it here, but I really won't go in depth. I do suggest you watch it. So I am starting off with the code from episode 2. This is episode 3. A couple things to note are that, first of all, I've got some new images here. Dirt. It's a little bit small. It's hard to see here. I can zoom in. It looks like dirt, grass, and the player, which is super small. There's a background of white, which is going to be important in a moment. And then here's my main script, which came from episode 2. So first of all, I do need to load the new images. So grass image. Do the same thing for dirt. And the one part that I am going to copy in here is the game map, which I really don't think is an issue if I copy. So the game map is just a massive two-dimensional list that is the map for the game. This is not a good way to make maps for platformers. It's just a good introductory way to make maps for platformers. I'll go over different methods later on. I don't remember which episode it is, but I think it might be the next episode I start using text files. But then also, even later on, I'll start showing you different ways to use tile systems where you can easily make infinite worlds that run well. It might be episode 7, I'm not sure. Anyway, so this is the game map. It's just a two-dimensional list, so a list of lists. Each list inside the main list is a row or just something on the y-axis. If you look, you can kind of see through the numbers there's a shape here. You can see the 2s and the 1s make a small curve right here. There's a little platform right here. The 0s are air, the 2s are grass, and the 1s are dirt. So you can imagine some grass on top of the dirt that's down here. There's open air and the platform. Each item in the list inside the list is one cell or one tile, if that wasn't clear. Since you can access lists like this, the effect is that you can get the value of one of the cells by putting in the correct values here and here. If you aren't familiar, you can get, this just gets the element of the list based on index, and since that element of the list is another list, you can just tack on another one of these, and then you can get the cell within that list. So since at the top level, each list inside this big list is a row, that means that our y-axis goes first and then our x-axis is second. So each time you go through the main list, you're going down one. So that's y. And then each time you go across within one of these rows, that's the x-axis. So yeah, this is how we access this map. That's the important stuff there. So I did take the code from the last video, so I do have a bit of this still. You can tell the player image is much smaller now, but we do want to take out that old code. So I'm going to take out that box we were colliding with, and I'm going to take out the bouncing. So now we're just something following. Something else I'd like to introduce here is the concept of scaling the display in a sense. I'm not making the window bigger. I'm changing the base resolution of the game essentially, so that when I draw the pixel art, it gets scaled up so the pixels are bigger. So normally the way you do this is you make a surface that's smaller than the size of the window, and then you draw all your stuff onto that, and then you scale it up and draw it onto your window. I believe in future episodes I'll be using the window size of 600 by 400 and the base display size of 300 by 200. Also, by the way, you're going to notice that I have a habit of putting spaces here now. It's going to cause some differences. So I'm pretty sure I didn't really cover this concept too much earlier on. You might have been able to figure it out, maybe not. But essentially, surfaces in Pygame are just images Like when you load an image, it creates a surface, and on that surface is the image. When I create a surface like this, it's just a black surface, like a black image with a resolution 300 by 200. When you create the window like this, you're actually also creating another surface. It's just that surface is the one that is being shown essentially, and the size is the size you give it here. So my point is that you can actually render one surface or an image onto another surface or image, which means that you can render the player image onto this black image that I just generated. And then what I can do is I can take this image and then scale it up and then render it onto the window. When I do that, it makes even though these images are small, it makes everything I render bigger. So it's a little bit abstract, but if you play around with rendering images onto the other surfaces and then rendering that onto your main display, I think you'll be able to figure it out. So you might want to do some stuff on your own where you play around with the idea that you can show images on other images and then use them for whatever you want. But yeah, I understand this is kind of confusing, especially if you're new, but it's a very important aspect if you want to do pixel art. So what I'm going to do here is I'm going to blit onto the screen the Pygame.transform.scale of the display, and then I'm going to scale it to the window size. So Pygame.transform.scale is a function that changes the size of an image or a surface. The first argument is the surface you want to change, and the second argument is the new size you want. So what I'm doing is I'm changing the size of my smaller image that I'm rendering everything onto to be the size of the window. And now that I've got this returns the new surface. So I could just do this, if that makes it clearer. And then I just put this at 0, 0. That means top left. Since our new resized display is the size of the window and we're just trying to put it onto the main window so people can see it, we render it at 0, 0 so that it's perfectly aligned. As the top left of this display surface should be the same as our window. Also, it's important to note that now that I'm using this surface to render everything onto, I do need to switch where I've been rendering everything. So instead of doing screen.fill, I do display.fill, and instead of rendering the player image onto the screen, which is the window, I render it onto the display. These variable names, display and screen, now that I'm thinking about it, it's probably not the best wording. It's just a habit I have. I always call my window the screen, and then the surface that I render onto that gets scaled up later, the display. So let's see how that looks now. So it might be a little bit hard to tell since I haven't run the game in a bit, but you can see the player's quite a bit bigger than it was before. So if I were to run the game without scaling everything, the player would be this big. And actually I can demonstrate this right here. If I just set this to the size of the actual window, it'll try to scale it, and it'll scale it up to this size, which is the exact same size, so it doesn't make anything bigger. So you can see it's much smaller that way. Anyways, let's go back to the resolution that I intend to work with, which is making every pixel twice as large. Okay, now time to do the tiles. So to render the tiles, we just have to iterate through our map, and then each time, like when we iterate through the map on just like a simple for loop, and then we grab the items in the map, we're going to get a row. So we have to do 2 loops inside each other. One to get each row, and then one to get each cell within each row, which will give us the tile type. So for row, I believe for future reference, I do call this variable layer, but code and layer videos may vary a little bit. It's going to be basically the same though. For row in game map, x equals 0, because at the beginning of a row, the x value starts at 0. I'm going to be incrementing it as I iterate through each cell in the row, and I just have to be able to reset it afterwards, and I'm essentially just resetting it here before I even do anything. I'm also going to set y equals 0 at the beginning, so that means that by the time I'm where my cursor is right here, x and y are set to 0. This is the rendering position essentially. So now I can do for tile in row. So the row is this, and now I'm iterating through that, and I'm going to get those cells, which are just the strings that contain the type of tile. So I can check the type of tile and then render things appropriately. But for the moment, I'm going to do something else. So for each tile I go across, I want to increment the x value by 1 because I'm moving across this list. So I process this one, that's x equals 0. I process this one, this is x equals 1, and then x equals 2. And then after I've completed that row and gone through this list inside the big list, I can increase y by 1 because I'm moving down to the next row or the next y value. The y starts at 0, never gets reset because there's no higher axis. The x value does get reset every time you go to a new row because you don't go 0 here and then there's no 0 over here. You have to reset the x value, so you start over here. Okay, so now we can render our tiles. So we have to check what type our tiles are. So if tile is 1, this is a dirt image. As you can see, it's all dirt down here, all those ones. I can render the dirt image now. So display.blit dirt image at the x coordinate times the size of the tile, which in our case is 16 pixels. That's an important thing to note if you're making your own images. You're going to want to keep track of what your tile size is. This is very important because in order to render tiles next to each other, you're going to have to offset them by their width and height. Keep in mind these x and y values are just the indexes or base coordinates of the tiles, so we have to multiply it to get the pixel coordinates of the tiles, which are based on the image sizes. So now that we've rendered the dirt, we can do the grass. So tile is 2. We can take this and just do grass. Actually, to make this clear, I'm going to just make a tile size variable. And then I'll pull it from here. Tile size equals grass image dot get width. That's just a function to get the width of an image. There's also get height. This will hopefully create less confusion if people start using my code. I've probably seen at least 5 complaints about people getting confused about that. So if tile does not equal 0, this is important. This is if the tile is not air. So that includes both 1 and 2 in this case. Then we're going to need to keep track of the tile for physics later on, because it's one thing to show all the tiles and it's another thing to have the player be able to collide with them. So we need to keep track of all these tiles so the player can collide with them. So I'm going to do is create a list called tile rects, and then I append to this list for every tile that isn't air. So tile rects.append, and then I'm going to make this a rect. I believe I covered this in the last episode what a rect is. So x by tile size, y by tile size. So it's x position, y position, which is the same position we're rendering it at. And then the size on each axis. So tile size, tile size. Also, just a quick note, this is assuming that the width is the same as the height. You can also have separate width and heights. So you could have tile size X, tile size Y. Anyway, so now we've got a list of rects that represent the positions of the tiles. It's important to note that in, I believe, the previous episodes, I actually rendered all of the rects. It's important to also remember that rects are just rectangles. It's what Pygame's native object for storing just a rectangle based on the position and the dimensions. But yeah, previously I rendered them. This time I'm not going to render them. They're just for the purpose of testing for collisions. Pygame has built-in functions for testing for collisions, which I showed you in the last video. It's .collideRect. So yeah, I just got a list of these and I'll use these for collisions. But let's take a look at our map now. Oh, I forgot. I fully spelt out image up here and then I forgot to down here. Normally I shorten it because there's a lot of images sometimes. So you can see the player just fell straight through. But you can also see that the terrain's here. If you look up to this map, you can see the resemblance. Also, if you notice, the player's got some white around it. There's all that white around the player. So one way to fix it is to open it up in some editor and make it transparent and whatnot, but I wouldn't recommend doing that. The best way to do it, especially when working with pixel art, is to use a color key. A color key is where you say a specific color is transparent. If you're familiar with green screens, it's not like a specific RGB value for green screens, but it's like if things are green enough, I guess, it's transparent. So it's a similar idea as a green screen, except in this case it's a white screen, and we're using a very specific RGB value that gets converted to be transparent instead of a wide range of values. So I'm going to make the player's image transparent, so that's going to be player image set color key, and then 255, 255, 255. That's pure white. So .set color key is what you use to set the color key for an image, so that Pygame knows that that color is supposed to be transparent. So you can see there's no white border now. Okay, next up is the physics. This is the complicated part, and I highly recommend taking a look at the other video I've got in the description. I'm going to go over it lightly here. So the first function we'll need is to be able to take a bunch of rects and test for collisions with them. So I'm going to do collision test. If you aren't familiar with functions, I recommend looking them up yourself because this tutorial is for people that do know a bit of Python. So the rect of the player is going to be an argument, and then all of the tiles we're testing collisions with. So this is just a single rect, and then this is going to be a list of rects. This is the player, this is the tiles. So we're going to have a variable for keeping track of all of our collisions. And then for tile and tiles, each tile is a rect, remember. We're going to be using this tile rects list that I'm adding to here for the collision tests with the player. That should hopefully clarify the usage of this function, or our planned usage for the function. So for each tile in the tiles, you want to test for the collision. So if the rect, in our use case, the rect of the player, collides with the tile, then we append the rect of the tile to our list of collisions. And now we can just return our list of collisions. The next function we'll need is the function that does the physics themselves. So tile collisions are very confusing to a lot of people because normally they try to do both axes of movement at the same time. I'm not going to go too in depth, but the basic concept is that you separate the two axes of movement, so the y-axis and the x-axis, and then you do the movement on each axis individually, test for collisions, update the position based on those collisions. It's like if you hit a tile moving right, you need to put the player's position on the left side of the tile, and then you can move on to the other axis. So we'll go x-axis and then y-axis. Like I said, if this is confusing to you, I highly recommend watching my in-depth video on this. So this is going to be called our move function. It's going to take the rect of the player, the movement of the player, and the movement of the player is just going to be x and y. So like, it's just a list with two values. And then all of the tiles we can collide with. So we need the thing we're moving, how it's moving, and the things they can potentially run into. I'm going to create a dictionary here to keep track of which ways the thing we're moving has collided. This is useful for just knowing like what direction things collided, because that's important in platformers, because if you collide with something on the side, that's different from colliding with things below you. Because in platformers, you're going to want to reset the vertical velocity when you hit the ground. Otherwise, it's just going to be kind of like you're always falling. You're not going to fall through the tiles if you do your collisions properly. Like if you walk off a ledge, you're going to continue falling very quickly instead of starting with a vertical velocity of 0 and then accelerating downward. So there's all sorts of reasons you might want to know what directions you've collided in. So collision types equals, and then I'm just going to write this out. Okay, so this is our variable for keeping track of our collisions. We're going to return this along with the object we're moving in the end. So we're just going to do return the object we're moving, so the player, and then the list of collisions that occurred, essentially, the directions. So now in here, we have to write the part that does the collisions. So like I said, you separate the axes and you handle them individually. So let's do the x-axis first. So we need to apply the movement on the x-axis first. So x plus equals movement 0. Now that we've moved the player on the x-axis, we can grab our list of tiles we may have collided with as a result of that movement. Hit list equals collision test. We throw in our player, and then the things it can collide with. So this is going to be a list of all the things that it collided with. So for tile that we collided with, now we have to update the player's position based on the way it collided with that tile. We know it's only moving on the x-axis, which means if it's moving right, the right side of the player needs to be set to the left side of the tile. I've got some illustrations of this type of thing, I think, in my more in-depth video. So if movement 0 is more than 0, that means you're moving right. Then Pygame has some really useful functionality for the rects here. You can set the position of a rect based on the sides of the rect. So I can set the position of the rect based on the right side of the rect. So rect.right, so based on the right side of the rect, I'm setting it to the left side of the tile. This is just putting them essentially next to each other, where this one's right side is touching this one's left side. So it's just player on the left, tile on the right. This is what you want to happen when the player is moving right and collides with the tile. I also need to take note of the fact that there's a collision on the right, so collision right equals true. That way this value that's returned will list a collision on the right is happening. So now I'm just going to quickly do the other direction. So elif movement 0 is less than 0, and then I'll write this up real quick. Okay, so that's handled the movement for the x-axis. And like I said, you handled the axis separately, so now we must do the y-axis. So update the y position. And then we have to, for the collisions based on the movement on the y-axis. So we're now in a different position than we were after we did this. So we have to check for collisions again because we may have collided with new tiles again. Remember, when we do this collision check, since we're only moving on the x-axis, all the collisions have to be a result of the movement on the x-axis. And now that we've processed these collisions, all the collisions here have to be a result of the movement on the y-axis. So for tile in hit list, and then we do the same thing again, except bottom with top and top with bottom. So if movement 1 is more than 0, so falling down, and we can then just do rect.bottom equals tile.top, collision types bottom equals true, and I'm going to quickly write the other part. Alright, that should be it for our move function. It updates the player's position based on the collisions, keeps track of the collisions that we did have. It processes the movement based on this variable. So now we need to put it all together and use it. So right here we've got our part where we're setting the player's rect to the player's location. I'm going to take this out. We don't need that anymore because the player's location, we're just going to store it in the rect. Normally in my projects I don't do this, but for the sake of this video, that's what I'm doing. So this is the movement stuff right here. So what we do need is a player movement variable. So it's going to be reset every frame to equal 0 on the x-axis and 0 on the y-axis. That's movement by default. So first, if the player is trying to move right, then we want to increase the intended movement velocity on the x-axis by 2. If moving left, player movement 0 equals 2. Remember, this is not the position of the player. This is how much we intend to move the player. It's the velocity. So now we also want to apply the gravity. So player movement, so the intended movement of the player, 1, so that's the y-axis, the 0 is the x-axis. First value is x, second value is y. Plus equals player y momentum. Some of the variable names are not going to match between this remake and the original video on this topic. So when you move on to episode 4, you're going to have to keep your eyes open for variables that may have been changed. I'd actually recommend just downloading the code from the description after you've messed around with the concepts yourself, if you want to keep moving forward with the tutorial series, because that'll get all your variable names right. I also want to take out this part where it's modifying the player location. So I'm going to move this acceleration to the vertical velocity. I'm going to put it here. So now we have this variable, player movement, which keeps track of the intended movement of the player for the frame. Because remember, it's reset every time and it's recalculated based on what the player is doing. One thing I'm also going to do is set a cap on the falling speed. So if player y momentum is more than 3, player y momentum equals 3. That's just because you don't, like, this number is going to keep increasing and you don't want it to go too high to the point where you're falling at like 100 pixels per frame. I'm making sure that the player can't fall faster than 3 pixels per second. So now that we've got our movement stuff set up, we can try and move our player. So player rect equals move, that's our collisions movement function. We're going to move a player rect by the player's movement, and watch out for collisions with all of the tile rects that we added here. I'm also going to move this rendering over to here, and then player location, that variable I removed, so player.x, player.y, or sorry, this is player rect.x and rect.y. Now let's see what we've got. This needs to be removed. I'm going to put that as just 50-50 because yeah, that variable doesn't exist anymore. Looks like I forgot an S right there, and I forgot some S's right here. Oh, I also didn't take the collision directions here. Make sure you set both values, or else the player rect's going to get set to the rect, like essentially a list of the rect and the collisions. So I think that's it. I've made a lot of mistakes here. There we go. Oh, and it crashed. And looks like I made a typo. Forgot another S there. And there we go. We've got our player that's moving around and is able to run into things. So now we've got to add some jumping. We've already got this vertical momentum variable, so I can just do if event.key is k up, player y momentum equals -5. So when you press the up key, I'm just changing the vertical velocity to -5, which is going to force the player to start moving up. And then this acceleration from gravity is going to fight against that and eventually pull it back down. Okay, so now we've got some jumping in our game, although there's an issue. You can just jump as much as you want. So now we have to essentially be able to check if we're on the ground. One important thing to note here is that because we're doing our collisions on a pixel basis, and when we increase our y velocity, it's less than a pixel. If our vertical velocity is less than 1, and we're on top of the tile, the less than 1 vertical momentum is not going to be enough to actually move the player's rect onto the tile that it's standing on top of, which means that we're not going to actually get a vertical collision every frame. Before I deal with that issue though, I'd like to quickly just use the collisions to reset the player's vertical velocity. So if collisions bottom, so if it collided with a tile on the bottom, player's y momentum equals 0. So that just makes it so that our rate of falling resets whenever we touch a tile below us. Oops, it looks like I made a mistake here. I put a 0 instead of a 1. And I was jumping through tiles. If you notice, my head gets stuck to the roof here. It's the same thing as what was originally happening here. Originally, I would just fall really fast, but now with my collisions bottom thing, I fall slower. I'm not going to fix this head issue here. You can fix that yourself if you want. That's an interesting problem for you to solve. Essentially, you just check if there's a collision above you and correct your y velocity. But that's just representative of the issue. So yeah, like I was saying, because a lot of time when we're standing on the ground, our vertical momentum is going to be less than 1. It's not going to collide with the tile, well, the player's not going to collide with the tile below that frame, because it didn't move an entire pixel. One way to deal with this is to just say, oh, I'm going to set the player's vertical velocity to 1 when I collide with something below me. That way, you'll always have enough vertical speed to collide with the tile below you, so you'll get a collision every frame. That's one way to do it, but I'm just going to teach you a game design trick for platformers here. In platformers, there's the concept of allowing the player to jump slightly after they've fallen off of a platform. It's just a quality of life type of tweak, and I'm going to implement it here. It's a different solution to dealing with this issue as well. So it fixes two problems at once. So the way you do this is you add an air timer. So air timer equals 0. This is how long the player's been in the air. Every time the player touches the ground, you want to set it to 0. So air timer equals 0. Otherwise, air timer plus equals 1. So like when you're in the air, you want to add to the timer. So it's how long the player has been in the air. And using this, you can make up for the fact that you're not actually going to get collisions every frame. With this, we're going to take, what is it going to be? We're going to move 0.2 pixels. The next frame, we're going to move 0.4. So that's 6. And then after that, 0.6. So it's going to take 3 frames to move 1 pixel because of if our y momentum is 0 to begin with. So it takes 3 frames for us to move that 1 pixel to get that collision. So what I'm going to do here is I'm going to say if air timer is less than, we could do like 4 or 5 here, but I'm going to do 6 because that's enough to actually give a decent benefit in terms of the game design issue I was talking about. So if air timer is less than 6, so you've been in the air for less than 6 frames, you're allowed to jump. So I actually can't jump a bunch of times, so now I can only jump once. And then you can actually jump a little bit after you've fallen off the edge. It's hard to notice here because 6 frames is a really short amount of time. If I want, I can set it to 12 or something, or 20, where it's a lot more noticeable. So I can go here and then jump quite a bit after I've fallen off. But I'm going to leave it on 6. Like right there, I think I jumped after I fell off, like maybe about 1 or 2 frames. Anyways, that was a very long video, especially compared to the original. The original was like 14 or 15 minutes, I don't remember. This one, my recording here is like 46 minutes. I'm going to trim that down so the video you'll see is going to be a little bit shorter because I've got all sorts of pauses. But that's pretty much it for this remake of episode 3. The source code's in the description. If you're having issues, I didn't actually have this back when I made the original episode 3, but if you have issues, you can head over to my Discord server. There's a link to that in the description. It should also be shown on the screen. I've got channels dedicated to questions. I might help you, and there are also plenty of other people in there that are capable of helping you, especially if you're at this level still. If you're interested in my project, you can check out my Twitter. And I also have a devlog series on this channel where you can see one of my favorite projects I'm working on. Anyways, that's pretty much it for this video. Hopefully I'll see you guys in the next video.